So we continue in continuation to where we are before the network cut off. We are sorry about that, and this is still on the concept of equilibrium. We have talked about the first type when potential energy is maximum. The second situation we have, which is case 2, is when it is minimum. So we draw the curve of minimum for potential energy. Sorry about that. We know how to draw a minimum. Let's move it up a little bit. And when it is minimum, we are plotting the graph of potential energy against the distance, which is, we now look for the slope we call the U by ds, just like what we have done in the first plot. So doing that, we draw a tangent line here at the base point. And if we go by the tangent line, we know at the middle point of the tangent line, the U by ds is 0, which shows that the P is what is minimum. So substituting that here at this point, done, it will be 0. The UDS at that point is 0, no doubt about that. So which makes that to be 0. So other points, like we've done the other part, we shift this to the right. I call that distance as x plus, and I shift to the left. I call it as what, x minus. So now doing that directly, we know if we've done this from what we have also studied, between this particular point, we draw out the tangent point. The tangent will go in this manner. So students just need to be careful about understanding all this concept very well. It's not about cramming. I don't like a student cramming. So when we draw the tangent line, not drawn to scale at this point, to just be complete opposite of what we have drawn in the first part. And we draw the tangent at the second point, just like that. So like that, we have the tangent. It goes without saying that at the first point here, which is the first point, you can see the angle between it, which this one makes the tangent is an increasing slope. We say the U by the x is positive. And because it is positive, we know the interpretation on that will be, it will give us what the formula of the force will now be negative to U by the x. And for the other point, which is x minus, you can see it will shift at the positive side there. What this means is that there's something will slightly be displaced back to this point. So as you move forward, it will move backward and come back to its equilibrium position. During the second one, when we are shifting that to the negative, this is a negative slope is coming down. You all know how to do that. Yes, and doing that, we know the U by the s for x minus will give us a still negative slope, and the force at that point will give us a negative times negative. From the formula you can see, which is going to give us the U by the s, which is positive. And what that means was for a neighborhood, within the neighborhood, if we move to the right, this will shift back to the point of equilibrium, we will displace back, and if we move to the left, it will displace back to the right. So which can still attain the point of equilibrium back, which is x naught, anyhow you want to call it. And that type of equilibrium that can always go back to initial position when it has been disturbed is called a stable equilibrium. So about the last type, let me quickly illustrate that. And when we say the potential energy is constant, when we plot the graph. So the graph we're going to plot now is the one that shows a relationship of potential energy with respect to what we want to do. So we have a constant graph, and without any further delay, we can do that. Now the third case, case 3. About case 3, excuse me, we are putting into consideration the potential of a curve that has a line. This is a straight line because we are talking about constant change. So we consider this particular point, which is constant, when plotting the graph of U against x. I hope students are following. This is just concept video of what you have learned before, I believe, in junior classes. So now about this directly, we can say at any point, maybe we put an original point, which is the midpoint, the x naught. We know the U by the s will still be what? With 0 at that point. If we pick any other point also, either to the right or to the left, it will still be 0. So at that particular point, whereby what any change in displacement of the body with respect to its potential energy is still going to give us the force to be equals to 0. Such part of equilibrium is called neutral equilibrium. So we can say when it reaches the end, it can either fall or here it continues to go up. It doesn't change anything. But within the neighborhood of this locale, we are taking what the particular function of what the u by potential energy by the displacement is still going to give us what you can see it's always going to give us what 0. So that type of equilibrium, like I said, is called neutral equilibrium. So students need to keep these at the back of their mind because a lot of cases in examination you've been asked about equilibrium, and most of the questions that have come from my experience I've seen is whereby you see different diagram and asking you what type of equilibrium is being given. A quick illustration I can give to that, not to waste your time, is a situation whereby we have a cone. You can see a cone in this particular form. You can have another cone that is in upside down. Anyway, I can draw this cone better, but just for illustration. So we can have a cone that is sideways in this form. So if we have these three conditions, this explains what we have talked about. Here you can see at this particular point, this is it. This is the point now. Potential energy here is maximum at this point because this is the base. Potential energy is maximum here. So you say this is what a kind of what unstable equilibrium. In this case, potential energy, which is the base of this thing, is minimum. And here, in this case, you said it is a stable equilibrium. And then the last type of situation, you can see the position of this thing or the potential energy is on what is slanted or is what is constant because it's lying in the same side as this slant height, as you can see. So directly we can say this type of equilibrium was placed in a neutral equilibrium. So students should be careful about the way and manner in which the definition can be given in terms of definition, and be careful also with picking answer so that you don't fall victim of picking the wrong answer. So the last part of all these that we have said out since morning is just to go to a quick illustration that we explain in details what we have studied. Now I told you these illustrations are not sufficient for you to prepare for examination, but it is only for you to actually have an idea. So it's always better for you to actually do more questions on your own and also watch the question and answer part of each of the sections on the channel. It will also help you. In that, we only deal with numericals and those things we've learned from concept class are now coming in question class, and this is what we have on the channel. So guys, we quickly move to the last phase, and that is the last slide of this section, which is on illustrations. As you can see, the first question says the kinetic energy of a ball of mass 10 kg, which falls freely from rest for 3 seconds is dash. Now, from what we have studied, we said the Ke or kinetic energy of a body, junior classes, is half mv squared. Directly, you can substitute the values of the parameter, and here directly you can say half of the mass was given to be 10 g or 10 kg rather, and the velocity here is not given. You are only given the time. So directly we can apply Isaac Newton law of motion, which you have studied. It is from rest. So initial velocity, everybody should know this is 0 meters per second. So directly we can say v square, or you can say v equals to 8. I can just do that. These are short things you can work motion in one dimension. We've talked about all these. You know the formula is v equals to u plus at, but because it is falling, we can take a what we say motion under gravity or free fall motion, which we have discussed. So directly I can say v equals to gt. You can just do that. So v is equals to gt here is going to give us our g is 10 times 3. Not given, but you need to know it is 30 meters per second. So directly, students should give that at the back of their mind. Times 30 all is square. So 30 squares are 900. 2 here 1, 2 here 5. 900 times 5 is going to give you 4,500 joules, which answer can also be in standard form, depending on the nature of the question. So the second one, my dear student, is a spring of force constant of 150. Remember, we have discussed force constant to be K, and we are given to be 150 Newton per meter. Is acted upon by a constant force of 75 Newton. Force is 75 Newton the potential energy stored in the string is such. This is on concept of what we talk about work energy theory, and we've talked about it. When a string or anything you call it is being stretched, elastic potential energy is stored in them. The elastic energy is used for work done. So the work done in them is in terms of elastic potential energy, and we have already studied that. So keep that at the back of your mind. So the potential energy stored in the string is as a result of the work done, which you need to know. So we say energy stored in the string, which is what the question asks for. There's always a potential energy that is used to do work. We say it's half Fe or half Ke squared. So keep that at the back of your mind. It's very, very important for you to know. So in this case, we are given a force, and we are given the what's it called, the force constant. So we've talked about this for you guys to know. So now half Ke squared or half Fe. So now using the concept we have learned, we say work done is stored in form of potential energy. So if we can tell that half what we have here is we have Fe. I think Fe we help us half Fe. So which I have talked about in concept class. What is formula for force times displacement is also equals to, you can see what we're talking about. We have half times the F, or you say Ke squared, which I think is even better here for the sake of the question. So what we do here is just to calculate the rest of the thing, is just to substitute parameter. So I hope you understand this. And if you have issues, you can always let me know. What I've done here is just bring up the first question of this, and you can get the extension if you need it. And if we don't want the extension directly, we can calculate the potential energy. Only the potential energy is asked in the question. So directly you can use half Ke squared, or you use half Fe. So potential energy stored in this is just directly half Fe. So if I go by that, I don't have the E, so I need to get the E. I'm running away from that. So how do I get E? That is what I need to do here. And we go back to our elasticity concept that says F is equals to Ke. I need to get my E there. So directly, let's do that directly together, because the question only asks for kinetic, the potential energy. So K from here, or E from here, is the same thing as saying the force divided by the force constant. It is 150. So this is year 1, year 2. Everybody knows this will give us 0.5 meter. So substituting that is what I was thinking I can do directly before, times the force here is 75. Multiply that by 1 by 2. So directly I've turned 0.5 to 1 over 2. You can use your calculator as always. So it's only the potential energy, not the work done. So here we can say 75 divided by 4, which I believe 4 can go in 7. It is 4 times 1, it means that 3. 4 7s are 28, 4 8 are 32, 18.75, 32, 30, 75. I hope students understand this. And we are talking about energy ratios. So be careful about conversion sometimes. Here, nothing was asked. Only what is asked is a direct question, calculate potential energy. And we know in the wire we store elastic potential energy. The next one, guys, I told you, I'm not the one preparing the slide. It's always prepared by the student. What I do is just come and explain and show. The next is we have a bullet, 0.05 kilogram, traveling with this speed horizontally, strike a thick vertical wall, and it stop, I don't know, after penetrating through the wall at an horizontal distance of 0.25 meters. The question is, what is the magnitude of the average force on the wall? A bullet is an example of a rigid body. We've talked about concept of rigid body as well. So we can draw the illustration if you want, and if you don't want, if you understand the work energy theorem, as is showing at the back, we have talked about a rigid body. We said work done is always stored in form of kinetic energy. And kinetic energy from early classes is what? Half mv squared. Now the work done is force times distance is equals to half mv squared, because in this question, we are asked to find the average force. So directly I'll receive the parameter force, distance of 0.25, fine. We have a magnitude mass is 0.05, velocity directly 500. So we can put the parameters and get it. So directly we can just say fine. The force is what we are looking for. The displacement or distance covered by this in the direction. You can draw the bullet moving and striking a vertical wall, and the wall, after it has struck the vertical, the wall was what displaced to another position. This is the way we do physics, but it is not needed, and that is why most of your teachers also, what teachers are really trying to be honest, that is why they don't show you all these things. What they just want you to know is how to apply the formula quickly to get answers. So now directly you can always have this, and you have a 1/2, or you say m is a 0.05. You are taking the square of v square. V is a 500 times 500. We are dividing everything here by 2. I can go by cross multiplication, and by doing that, I have f times 25 twos are 50, 0.50. So I can make f subject of the formula. I hope students can do this. And by doing that, I can say this is the same thing as 0.05 multiplied by 500 times 500. We are dividing the answer by 0.50. So directly, we can just punch a calculator. Doing so directly, I'm trying to get a calculator, and I have one here. So I don't want to waste my time or stop myself breaking anything down. Though we can do it without calculator, as always, but I'm not feeling like doing that. So from my calculator directly, what I have here is a 25,000 application force, which is always measuring what Newton. Force is measuring Newton. Keep that at the back of your mind. The last for this question slide is a ball of mass 100 grams falls from a height of 5 meters onto the floor and rebounds. You can draw the illustration to a height of 3 meters. What energy is lost in this? You can see nobody asks you to calculate what work. It's just like I think the second question I did. It's just the energy. Two things are involved. There is a ball and there is a ground. There's always a ground. There is a ground and there is a ball that was dropped from, let's say you are here, you stretch forth your hand and you drop a ball, and when the ball reaches the ground, it will bounce back to a particular height. This is 3 meters. The first height is 5 meters. This is some illustration. So what we can say is that the energy gain here is this has gained kinetic energy. Keep that back of mind. So the kinetic energy gain in it is what you can say there are two ways. The first one, kinetic energy is half mv squared, and the second kinetic energy is half mv squared too. But we are looking for loss of energy. So that means we are going to subtract. So we are subtracting the two energies from each other. So directly we can just put the parameter. So that's that. You can do it by one. And if you don't want to waste your time, you can just do it directly. Get the velocity in each of them. It is gravity free form motion. Velocity equals to under root of 2gh. So if you look at my formula, I'm having v squared. So I can just say v squared equals to 2gh. For the first one, I have 2 times g is always 10. 2 times 10 times 5. You can see 2 times 10 times 5 is going to give me 100 meters per second. And the second one, the same formula, v squared equals to 2gh. U is 0. That's why I'm not putting u squared in the formula. So directly I can say 2 times 10 times 3. Our students are getting this, and this is giving me 60 meters per second. So directly we can now solve and substitute here. We have ke in this direction will be half, and say half, the mass is uniform, m open bracket v2 square, or you say v2 square minus v1 square. And if you don't know how to factorize, you can do it one by one. So doing that, my dear students, directly you can just say here is just ke will now be equals to 1/2 multiplied by your mass. Remember, this mass is in gram. You have to convert to kilogram. That is 1 kilogram. 1,000 grams make 1 kilogram. Divide by 1,000 grams, 0.1 kilogram. I have converted the mass from 100 grams to 0.1 kilogram, because 1,000 grams make 1 kilogram. So here I'm taking the difference of the squares of this one. So I can just say, for my way of understanding, it seems as in 100 minus 40 all is squared, which is the same place. Now directly I can just say this will give me 100 minus 40, 100 minus 60. per square. So 40 squares are 1,600 or 1,600, you can call it, and multiply it by 1,600. 2 can go here. This is 800. So what you have is 800 divided by 10, or 800 times 2.1. And that is going to give me 80 joules. So that is the answer to this question. And that is the end of the video section. So the next one, which will be the last slide for this, the next video is going to talk about the last aspect of work energy. Then now we have power. So we're going to discuss just one video on power, and that will be all for work energy and power for our from us. So the rest will be on calculations and the numerical on this chapter. We can also get. Bye for now. Enjoy the